next we're going to talk about counting. Counting is very important. Some textbooks would have counting as its own little chapter. Some textbooks would introduce counting first because we can use counting to come up with some probabilities. Okay? So there are lots of different rules. I think, I almost don't want to say this in the recording, but I think the author got a little tired of writing. He just said, here are all the rules. Here they are. Like me. And then, he was tired. I don't know how anybody can write a book, so I admire him for that. But we're going to talk first about this fundamental counting rule. Okay, fundamental counting rule. And I think I mentioned this in class the other day, but let's just take them one at a time. Fundamental counting rule says the number of ways that two events can occur together, given that the first event can occur in m ways and the second event can occur in n ways, it'd be m times n. Okay, a very simple rule, but very, very, very powerful. So let's look at some examples of the fundamental counting rule. Okay, it says you're purchasing a new car. The possible manufacturers, car sizes, and colors are listed. So you got manufacturers Ford, GM, and Honda, car size, compact or midsize, color, white, red, black, or green. How many different ways can you select one manufacturer, one car size, and one color? Okay, it says use a tree diagram. We're not going to do that. But I've got some choices to make. He's called them events. They're not parties. They're just things we need to make choices about. Okay, so I've got to make a choice about the manufacturer. I got to make a choice about the size, and also a choice about the color. Okay, but whatever number of ways those things can happen, I multiply that together to figure out how many ways it could happen altogether. Okay, so how many choices do I have for manufacturer? 3. For car size? 2. And for color? 4. So we get 24 different ways in which we could select a car. All right. You like that one, okay? Remember, we talked about this the other day. Remember we said in a family of 3 children, how many different ways could you have, boys and girls, right? 8, right? Because the first child has 2 options. The second has 2 options. The third has 2 options. And so there are 8 different ways. And we actually listed the 8 different outcomes, okay? All right. Another example, there are 8 different stats books, 6 different geometry books, and 3 different trigonometry books. A student must select one book of each type. How many different ways can this be done? Okay, well, we got to make a choice about what? Okay, which geometry book, which she just skipped right over the stats book. But it's going to be in there. And also the trig book. Okay, whenever we get that, we'll multiply those together, and that'll give us our answer. So we got how many stats books? 8. How many geometry books? 6. How many trigonometry books? 3. What is it? 144. Okay, very good. Okay. Okay, that's interesting. I think we got it, right? Okay, so let's not do this next one. Let me go off script and consider some things. I think I told you all about my license plate dilemma. Did I tell you about that? I don't think I mentioned that. Driving up and down the highway when I was living in Orangeburg, and they have the sunrise license plate, right? And I noticed it because I'm always noticing patterns, and all of them started with an A. And I was like, oh, that's interesting. So I had a theory. I was like, are they distributing these things alphabetically? I got excited. And so I watched every day until finally I saw a B. And I was like, yes, they are. Yes, they are. And why did that excite me? Because now I can count how many license plates they can make. Okay? Otherwise, they were, no, well, really, well, I'm sure somebody's counted it, somewhere. And so I can count it too. Not one by one. I'm going to use fundamental counting rule. License plate has 3 letters. I won't tell y'all what mine are. And 3 numbers. Okay, 3 digits, we should say. Right, she's still in disbelief. But it's true. Okay. Did y'all not notice that? Yeah. Okay. Yes. Yeah. Oh, me too. We do that all the time. Yeah, but I think a lot of them I would like to think a lot of them that they skipped. Some things, I'm thinking they wouldn't put up there. There's one I'm really concerned about. We're gonna see it another year or so if they put it out there. But anyway, all right, moving on. We digress. So, all right, how many choices do I have for the first letter? 26. Now, and then for the next letter, 26, and the next letter, 26. It is fair game and knowledge for the test that there are 26 letters in the alphabet. Okay? All right? Just sometimes we had confusion about that. How many digits are there? Well, choices for a digit would be 10. Okay? And so we multiply those together. 26 times 26 times 26, or 26 cubed, times 10 cubed. Oh, yeah. Okay, I got, 17,576,000 license plates that they could make using this particular scheme. Something interesting has happened, though, because I've been watching for several years now. Well, first of all, they got off track, and they made a TGR tag, which I'd love to have one. They made a USA tag, and they also made a USC tag. Those are out there. Yeah, I want to know how you can get one of those. I want the Tiger one. But I was thinking there are only about 4.5 million people in South Carolina. Not all of those people can even drive, and even all of the drivers don't necessarily have a car. So, yeah, some of them might have more than one car, but still, by the time you balance that with people who can't drive or don't have a car, I predicted that we would never get past G, I think. And I said that because if we limited the number of letters, to just the first 7, then instead of 17 million, we're going to divide this by 26, then I'm multiply it by 7 instead. We come up with 4,732,000. I thought that'd be enough for South Carolina. So I can't quite figure out what happened, why we're still generating these tags. So if anybody can get me an interview at the Department of Transportation, I have some questions for them, okay? However, this gets to be interesting. What if we decide that we don't want to repeat letters, okay? So here we allowed repetition, but no repetition. Let's say digits can be repeated, but no repetition of letters. Right. That's true. I mean, but still, we're beyond 4 million in like a few years. Where are all these cars coming from? Not to mention. Okay, maybe so. Okay. But then there are other tags too. That's not the only license plate, so not everybody's getting that one. Something else that was interesting was I think you can pretty much identify the county in which the car was registered by the license plate. Okay, they didn't pass them out one by one. They sent Orangeburg County a box of whatever, and so whatever. And of what? Of A's, okay. And so then I even had a student who worked for UPS or someplace like that who said he came in, he was really excited. I had a box, it was busted open. All of the license plates started with the same letter. So we were really excited about that. But anyway.
But it was designed so it would never run out. I looked at it myself because I thought to myself, it was
Maybe like 4.
Yes, ma'am. And so it was designed so it wouldn't ever run out like that.
Maybe so. But eventually it is going to run out.
It's designed for it to run out when they're going to replace it.
When they're ready to replace it, right.
And that's based on the
Usually about 10 years, right. Then we get a new plate altogether. But anyway, let's say we don't repeat letters. Then we have how many choices for the first one? 26, okay? Once we've made a decision about that first one, then how many choices could we have for the second? 25, and then 24. And let's say the digits are repeated, so it's still 10, 10, 10, okay? You can multiply that out, and that's how we would figure out how many possible outcomes there are if we allowed repetition, okay? One more favorite example is, most people in here are too young to remember this, but it has to do with area codes. For years, South Carolina was only 803. And then, you know, once people start getting cell phones and pagers and all these different things, we needed more area codes. And the same thing happened in other states. But the rules for area codes were, first rule was it could not begin with 1 or 0. Okay. The second digit had to be 1 or 0. And then finally, it could not end in 0, 0 or 1, 1. Those were reserved for special things. Okay, but pretty much that summarizes what the rules for area codes, telephone area codes were. So under those rules, how many area codes do you think we could generate? A lot, okay. That's not going to be a choice on the test. How many choices do we have for the first digit? 8. Very good. Okay, 8. Can't be 0 or 1. All right, how many for the second digit? 2. Had to be 0 or 1. Think carefully, very carefully, think carefully. How many choices would we have for the third digit? I've heard some answers of 9. 9 is right. Okay, I could put a 1 here. Once I put 1 here, 0's fair game over here. So there are 9 choices. If I put 0 here, 1's fair game over here. 9 choices. And so when we multiply that all together, we get 144 different ways. I don't know. It hasn't been that long. Well, 10, 15 years, I don't know. 864. Yeah, those. Well, I don't. Must be this. Well, yeah. Now you could have anything in that middle digit. Yeah, that's what it is now. Okay. Here's another scenario. I really am teaching. These are not just like memory lane. Let's say you got a dinner party. 1, 2, 3, 4, 5, 6. I need y'all to stop talking, please, and listen. Let's say we got 8 people at our dinner party. And you've gotten everything done, and you can sit down and think about how many different ways can I arrange these 8 people around the table. Okay? So you got 8 chairs, and you're thinking, well, I have how many choices for the first chair? 8. Okay? And then once I assign a person to the first chair, how many for the next? 7, 6, 5, 4, 3, 2, 1. Different ways. Okay? So by fundamental counting rule, whatever that comes out to be, Okay, we're not going to take time to put it in right now. However, that brings us to the second rule in the author's table. Well, the second one we're going to talk about. It is number 2. It's called the factorial rule. Okay, the number of different permutations or arrangements. Okay, we're actually concerned with really swapping people around. It's the same people, but how many different ways can we arrange them? Okay, if we have n items and I want to arrange all n of them at a time, then we would say it's n factorial different ways. N factorial is equal to 1 times 2 times ... times whatever n is. It's the product of the first n integers. Okay, and it should be noted that 0 factorial is defined to be 1. So back to my dinner problem, instead of doing it by fundamental counting rule, I've got 8 people. I want to arrange all 8 of them around the table. It's 8 factorial different ways. Okay? And thankfully, our calculator has this built into it. Okay, we hadn't done a lot with the calculator, but we're going to do a bit now, right here at the end. Okay, so on the calculator, I'm going to put in 8. We'll go to math. We're going to go over to this probability menu, PRB, and you can get there in one step if you hit the left arrow. Okay. And then number 4 has that exclamation mark. That's the factorial symbol. Which part? Okay. And so there are 40,320 different ways in which you could arrange 8 people around your table. Yes. Then if we're interested in arranging all 9 of them, okay, then I would assign one seat to be empty. So that almost counts as like a person. Which one's going to be empty? So we'd say 9 factorial. This is a good question. Okay. So 40,320 different ways.
And you would do it the same just because that empty seat could be one?
That's right. We're assigning a seat to empty. Okay. All right. So now here the key is, this is almost a whole flow chart of its own. Fundamental counting rule, we're interested in how many different ways things can occur together. Factorial rule, I have n objects, and I'm interested in arranging all n of them at a time. Okay. Let's say we got 5 groups that are doing presentations at the end of the semester. Okay. And I want to know how many different ways can I have these groups present, in how many different orders. If we're talking about all 5 of the groups, it'd be 5 factorial. Okay. 1 times 2 times 3 times 4 times 5, which comes up to be 120. Okay. All right. At one time. When we talk about factorial, we're arranging all of them at one time. In comparison, let's say you have not arrived yet, and you don't have 8 chairs. All right, you only got 5. All right, then we're not arranging all n of the objects. We're just arranging 5 at a time. Okay, so in this case, we got 5 chairs, but I still invited 8 people. Okay, because I just had to. So how many choices do we have for the first one? 8, 7, 6, 5, 4. Okay? We can kind of force this to be factorial. You don't have to really understand this, but I'm just going to multiply top and bottom by 3 times 2 times 1. So that I can say 8 factorial over 8 minus 5 factorial. Okay? Formula doesn't matter because the formula is built into your calculator. The situation here, which is called permutations, okay, is we've got so many objects, n objects. but we can only arrange R of them at a time, something less than N. That's a permutation. And with permutations, what you need to repeat to yourself, as well as factorial, is that the order matters. All right, when we come on Tuesday, we'll talk about a situation where order does not matter. Okay, but for my dinner party, I want to show you this on the calculator. I would say I have 8 objects, and I'm choosing 5 of them at a time. Well, permuting 5 of them, if that's a word, at a time. And so on the calculator, I would do 8, math, going over to PRB. Number 2 is NPR. We're choosing 5 at a time. And so 6,720 different ways that I could choose to decide which 5 people are going to sit down and in which order.
Excuse me, is this going to be on the
This video? Yes. Okay. Let's just look at one problem, then I'll set you free. Yeah, oh, you're going to get your money's worth out of the calculator. Okay. All right, right here. Let's look at this one. 43 race cars started the 2007 Daytona 500. How many ways can the cars finish first, second, and third? So the way that I process this in my head is that we got a set of cars, 43 of them, but I'm only interested in arranging 3 of them at a time. Does the order matter? Yes, there's a difference between first and second place, right? So if I swap people, say, don't ask me to name people, but this person, number 43, whoever that is going to be first, and the other person is going to be second, Dale Earnhardt or something like that. Always swap them back. It's a different arrangement, right? And so in that case, that's a permutation. So what I would say is 43 P3, because we're arranging 3 of them at a time. And so on the calculator, we do 43 math PRB. Number 2 is NPR, 3 at a time. Well, N is the number of items that I can arrange, that I have available. P says I'm doing a permutation, and R says this is how many of those I want to arrange at a time. So N for us was 43. There were 43 people in the race, and R was 3. We wanted to arrange 3 of them at a time. Okay? All righty. We got a lot to talk about next week. I know your weekend is already planned for you.